Hey folks, welcome back to Advent of Code in F#. We're at day 12. I already did some preparatory work. I solved part 1 by using a brute force, and then I looked at part 2 and nope, brute forcing will not work. So this is what we'll be doing during this video. Quick recap of brute forcing part 1 and then taking a look at how we can solve part 2 in a reasonable amount of time. Something is happening with my computer. Let's take a quick look. Okay, everything's under control. Let's dive to the code. So day 12 is hot springs. It's the one with the cogs and the records and the unknowns. And we kind of have to figure out whether or not, or how many valid combinations are possible given these group counts and unknown locations, which are marked with a question mark. So that's day 12. Part 1, I solved literally by brute forcing, by generating all possible combinations for every line and verifying whether or not the counts are valid for that combination. So let's quickly go over the code. So we parse our inputs into a structure containing these character union types, which is a question mark, a dot, or a bang operator, or a bang, which is a cog or a spring. So that's what our parser is doing. And yeah, our sizes are just a comma-separated list of numbers, so it's an easy parse. This is a function that generates all the possible combinations, which is a recursive function, and it takes a look at the input characters. If it's the empty list, we return only a list with only one option, which is the empty list itself. So this is a bit of a funky way, but if you look at the return type, it's a list of characters. So that's why we have to return a list with only one option in it and not just the empty list. That's one of the recursive gotchas I run into a lot. Then if we encounter an empty character in a non-empty case, or if the character list is not empty and the first element is an empty, a dot, then we can just continue on. This leaves no room for optionality. It's just taking this empty and continuing on with the rest of the input string. For springs, idem dito, same case, we just continue on. But for unknowns, we split like into two possibilities. We like act as if this unknown is empty, and we act as if this unknown is a string. And then we call this function recursively, which will match one of these cases. So this is essentially splitting up the search space into two different subtrees. And this is what makes the brute force approach, or at least this a brute force approach, where we generate combinations and then check their validity, very inefficient for part 2. But for part 1, it works. And this is the function, this valid combination is the function that checks whether or not record adheres to the sizes provided in the record. And that is a bit of a beast, but there's a quick shortcut I take here. It's like if the total amount of spring group sizes is bigger than whatever we have left, we know we can never satisfy. So we break out early with a false, and otherwise we take a look at what sizes we need to do. If there's no more sizes, then the entire remainder of the string has to be empty. Otherwise, we kind of have to take a look at what we're looking at. And we don't expect any unknowns here because we just replaced them with a valid combination generator or a combination generator. So we don't expect those to be in here. If it's empty, we can just skip to the next character. And if it's a spring, things get a bit more complicated in my algorithm. But basically, we're looking at, okay, if we encounter a spring, we need to encounter n springs, where n is the next number of sizes, which is this s here. So we're taking a look at, are the next n characters a spring? And the next one has to be a dot or an empty space. And that's a bit what we're seeing here. So every group has to be delineated or delimited by an empty, and that's what this second pattern match is doing. So there has to be a dot after every group of springs. Otherwise, it's no no good. If we're at the end and we have nothing remaining, it's also good. So there's a lot of edge cases here, but I'm not going to dive too deep into this algorithm because it's not gonna cut it for part 2. It's too naive, it's too brute forcey. Quick look at the solve function. We just generate all combinations eagerly. This is a list, so we're generating millions of combinations for the second part, not tractable. And then we just, what are we doing? Yeah, we basically, for every combination, we count, or we filter out the valid combinations only, and we count them, and that's the end result. But as I said, this does not work very well for part 2. It will keep running until the heat death of the universe, I'm guessing. So we're going to take a different approach for part 2. I've seen a lot of people solve this problem using dynamic programming. It's a very fancy way of filling in a table with intermediate results and growing that table. I don't feel like doing that. It's been 11 years since I've last tried that, and I was still in school. So I'm gonna do something else. I'm gonna do a slightly better recursive function, not generating all combinations and checking their validity, but just doing it in one go. So not first generating the huge amount of combinations and then just filtering them, but in one go trying to figure out the number of combinations. We don't need to know the exact combinations, we just need to figure out the number of valid combinations. So that's the approach I'm going to try. And that will not be fast enough as well, but that's going to be a lot faster than this, and then we can start to apply some functional programming tips and tricks to speed up computation of recursive functions that do a lot of the duplicate work. But we'll get there when we get there. Let's first rework our algorithm so we don't generate and check, but we just count instead. I hope that's the plan. So let's take a look here. I think we can rip out almost everything except maybe the parsing. Let's keep the parsing. So instead of generating checking, we're going to count. Yeah. So we're gonna map every record to the number of combinations that that record can represent, and we're gonna sum those. And that's a function we don't yet know. We're going to write that one right now. So let's get rid of all this. Let's make it recursive. There we go. So this should all compile. This replicate thing is for part 2, where we have to grow our input. So let's keep that as well. Let's maybe take a quick look at that, because it might be interesting. If you have not used the replicate function, it's basically taking a count and an initial value and replicates the initial value n times, or count times. So we're using this to grow or to multiply our input, and we can flat map or flatten the list of lists by using this trick we've seen before. This is a flat map, and we just feed in the identity function. So that's a way to multiply a list n times in F#. And we do the same for sizes, of course. Why am I doing this funky thing? Oh yeah, because we have to delimit. You can do other things. I've seen people that use Python use join. I don't know if there's a join equivalent in F#. To join sublists together with a delimiter. Not sure, actually. No, I'm not sure. But anyway, this is how I replicate my inputs. And I think we can still use that if we have a very, very fast rewrite of the count combos. So let's make it work first, and let's make it fast next. But let's first focus on correctness. Record is a thing that has a list of characters and a list of integers, which are the counts of the groups of springs. Okay, yeah. So it's the characters and the sizes. And we're gonna be able to pattern match on sizes. That's something we can still do. if we're done, if we have no more sizes, then every character has to be either empty or a question mark, which can fill in as an empty. So character has to be this or question mark. And then what's the problem? Okay, no problem. So if we have no remaining group sizes, we can just say, okay, we're done if we don't have any springs in there. Otherwise, we have a size and the remaining sizes, and then we can take a look at what's in the characters. So we know we have a non-zero group somewhere in the remainder of the string. We need to find the first spring. The first spring is a... what am I doing here? I should use my union type. Sorry. So that's empty or unknown. So we need to figure out the first location or the first possible location of a spring. We know nothing. We know we have a group and we know that we are out of characters, so we know we are not finding any relevant combos in this case. Otherwise, we have a character. If that character is spring, we know we need to be able to consume S characters in this thing, in this characters, followed by a dot or the empty list. And then we know we have fully consumed this S. And we have one combination. That's only for the spring things. For the unknowns, it gets a bit more tricky, I think. Yeah, for the unknowns, it gets a bit more tricky. Interesting. I thought I was going to be able to hammer this out in 2 seconds. Well, joke's on me. Joke's on me. Okay. So if we hit a spring, we definitely know the first S characters have to be a spring. So and we have to take S minus 1, and those all have to be springs. Or unknown, that's also fine. This can go out of bounds. So if we don't have enough characters, we have a problem. So when this has to hold. Otherwise, we have a problem. So let's use a pattern match, a catch-all. So if these are all springs, then we know a couple of things. We know that the next thing has to be the end or an empty character. Yeah. Yeah. So that's I'm seeing too many red lines. So I'm gonna first satisfy the compiler. It's not satisfied, why not? Oh yeah, because this is, if this is true, then I need to return counts, not booleans. So let's return counts instead of booleans. There we go. Now I hope my compiler, okay, my compiler is shutting up. Cool. So everything is still correct. This was getting a bit too complicated, so let's recap here. Okay, so we're in the case where we have a group, a number, so a number of springs we need to encounter. This is a problem case, so we have no combination that's valid. Cool. If we have spring and we have enough stuff in there, and if they're all springs, and the next thing is the end of the list, so characters or CS consumed, the remainder of this thing. Yeah, okay. So, or the next character of after this thing is a dot, or it's done. So skip s -1. Can you split at? That might actually be better. So we only have to do the split once. Otherwise, when you do the skip and a take 2 times, it's a bit more expensive. So sub rest. This splits the list into a tuple of lists. Yeah, so that's a sub list and the rest. This is what we want here. And here we can use next is the rest. Yeah, okay. And rest can be end of story. Then we can just go on recursively and we hope that SS is empty. Yeah, we can just do the recursive call. So characters is empty and sizes is as is. What am I saying here? So incomplete parameters. Yeah, sure. I'm saying split my remainder characters. Give me the first s -1s. Yeah, they all have to be springs. Yes. And if that's the case, then we take a look at whatever follows. If we're done. Yeah, let's not do the recursive call. Then SS has to be empty, right? So then if SS, then we have a valid, otherwise we don't. And if we have empty, or we have unknown, that's okay. Then we can do the recursive call, because these we can treat as empty. Yeah, so then we know we're good and we can continue by counting combos for rest. And what's the remainder of the sizes? That, so we consumed the S fully and we're taking a look at the rest. Yeah. What is the problem here? No problem. And we can do the same here. We don't need to use rest. We can use RS here and there. Okay. So in all other cases, it's basically whenever we have a cog in there, I think. So if we have a spring in there, sorry, we have a problem. We have an invalid situation. Cool. If they're not all springs, then that's a 0. That's true. Okay, so that's the spring case. We encountered a spring, cool. If we encounter empty, that's also easy. We can do a recursive call. on the rest of the things and original sizes. Nothing changes, we forget about empty. And now there's the only tricky part, which is what happens if we see an unknown as a first part, as a first element in the character list. So it's an unknown. I think we can do the hack or the trick I did for part 1. If it's unknown, we can just split the search phase into 2 and take it like that. So spring, so we can do a recursive call saying count all combinations for my inputs where this is a string and all the rest stays the same. And my counts all stay the same, so that's sizes. So this is the combo count for the unknown as a spring, sorry. And that's as empty, same thing. We can just forget about this thing because we're gonna throw it away if it's empty. So yeah, that's those two, and then we can just sum those up. And that's not tail recursive, so I'm not sure how this will affect my optimization. But yeah, then we just return the sum. Can we make this tail recursive? No, it's going to be very hard. But in theory, that's the count. In theory, I think this might be correct. Zero testing again. It's an interesting year for me. Okay, so let's try to run our non-replicated example. That should give 21, right? It's still giving 21, so that's reaffirming. Let's now replicate 5 times. Ooh, I like it. This is actually 1 million times faster than my previous attempt, so that's good. But probably for my input, it'll be slow or too slow. But let's no, let's not check in. I know what I'm doing here. Famous last words. So let's run this on the input to make sure our CPU burns. I think it's burning. It's very much burning. Memory is not too bad, actually. Interesting. Okay, but I'm gonna cut it off before my video capturing software crashes. But we're in a much better place than I was during the brute force approach. So I am happy. I'm gonna commit this. So we're not there yet, but we're one step closer. What we did is rewrote our logic to not generate, then check, but now we're just counting with this beast of a recursive function. It's not a pretty function, oh geez. But I'm not here for style points, I'm here to actually get my star. One thing we can do now is, because it's still very slow, but if you look at what it's actually doing, if you start printing out or if you start manually drawing, it's actually doing a lot of double, triple, it's doing a lot of repetitive work. It's taking a look at a lot of inputs that have the same, it's counting this, it's calling this function recursively with the exact same inputs a lot of times. And there's a technique called memoization, which is basically remember every result you get while you call this function and just plug them into a dictionary and first look up if you've ever calculated this value before you actually do the calculation. And it's really tricky if you try to do this with immutable data structures only. So I'm going to do a 2-step approach. I'm first just going to use a dictionary, a C# dictionary, which is mutable. That'll make memoizing our function here way easier than using an immutable approach. So let's memoize count combos by using a C# dictionary. here we go. So this is the function we want to memoize, and I'm just gonna wrap the entire body into an inner function, and that function we're gonna have work on, or that function will know about the memoization table. So I'm just gonna call it calc. I don't know why. And it takes a memo, which is our lookup table. And let's extract function, and let's call that calc function. I need to, there we go, with the memo and the characters and the sizes we get. And then wherever we do the recursive count combos call, we're now gonna do calc, which is that inner function. So now we actually did nothing interesting, we just extracted a function. And we need to provide a memo in all those cases. Oh boy. Oh, shoot. That's not something I like to see when I'm using memoization. Let's take a look at whether or not we can rework. Yeah, okay, everything is compiling. Would this actually work? Yeah, it would work. If it's a shared data structure, so recursive calls can use that dictionary. Actually, this will still work without any rework. If we use a mutable dictionary at least. So yeah, let's do that. Let's define our memo. I'm gonna provide a type alias so I don't have to type the entire dictionary fully qualified name every time. So I'm gonna open the namespace. What is it? I think dictionaries are in here, in the C# or the .NET system.collections.generic, and it's a dictionary. Yeah, there we go. And if you look at memoization, what it actually means is remembering for each input the output. So we're gonna take the type of the input as a key and the output, which is our count, as the value. So that's an int, and the key I forget. So let's take a look at what the input is actually representing here. So it's characters and sizes. So that's a tuple containing a car list and an int list. We can just, there's great interop between C# and F#, so we can just use those types as keys in our dictionary here, and it'll just work as we expect. As long as, yeah, it'll work. Not no as long as. So if I provide memo a type hint here, that it's our memo type, and then lean on the compiler to fix all my compiler bugs, and pass through memo. So that's one step to making this function memoized. And this is the outer call, or the initial call. So we need to provide an empty memo here, and that's just a new dictionary or a new memo, because it's an alias. This will work. So this is just newing up a C# dictionary. There we go. We have a dictionary in there, but we don't do anything with it just yet. So let's start checking it and start inserting values. The checking it is really easy, so let's do that first. I'm gonna grab the entire inner or implementation of the calc, indent it one more so I can wrap another pattern match around it. There we go. And we're going to check the memo. So we're going to try get the value out of this dictionary, and we need the key. So let's define key, which is our input tuple. There we go. We're going to try to get the key, and if it's in there, so that's if the try get value returns a true, we know the result, which is the count which we have calculated in the past. So that's just return the result from the dictionary. If we don't have anything in our memo, we need to calculate it and put it in there. So that's what this second arm of the pattern match is all about. And this second part is actually calculating it. So this match statement is the value we want. So let's just catch that. And let's return that. And before we return it, we can also add it to the memo. So we add our key and our result just before we return it from this function. And this is everything you have to do to memoize a function if you use a mutable dictionary at least. So cool. Let's see if this works. Let's do it for the example first. Let's maybe first check whether or not our approach works without replicating. So I'm gonna use records. Should still be 21, right? It's still 21, I'm happy. So let's now replicate and use the replicated input. It's a biggish number. We already knew this worked, right? Yeah, we've seen this. But now for input, it should also work. So this was a bit of a regression test. My memo refactoring has not broken anything. So now I'm pretty sure this will go a bit faster, or at least I hope it will run in a faster runtime. Oh no, it's not, it's crashing. Ooh, it's resulting in an overflow on line 86. Interesting. Oh, really? It's probably the sum, so I'm gonna put the sum in comment for a second, so it's bigger than an integer. That's probably very logical, yeah. Let's see if this works. Yeah, okay, so it's the effective problem is doing a sum or list.sum on all the intermediate results. If you take a look at sum, it returns no, the problem is that it returns a t, so it's generic, it should work, but the thing we have here are all integers, and that's the problem if we try to sum integers to something bigger than an integer. So we can fix this by just making those integers into longs, which is int 64, I guess. And then it should work. Because list sum is generic, this should all work nicely together. Let's see if we still get the big number for our example. Yes, we do. So I'm comfortable to run this on our input. And we are sub-second, so I'm very happy with this. I'm pretty confident that this will work. And the confidence was unwarranted, of course. Interesting. What was the actual problem we got? It's not the right answer, or was it... Do we get a hint, or whether or not we're too high, too low? Now I have to wait 40 seconds. Interesting. I would have thought actually this was in the bag, as they say. That's a shame, that's a shame. Why is there a bug for input, and why is it giving me the correct results for the example? I hate it when that happens. Don't you just hate it when that happens? 525152. Yeah, that's super correct. Is my trick to convert to a long here correct? Maybe we can just work in longs everywhere. Yeah, I'm willing to give that a try. So this can be an int 64. And wherever we return values, we're gonna return longs instead of integers. Yeah, I'm on track. I was second guessing myself. So this should all work. What's not to like here? Yeah, what's not to like here? Oh, there's some more integers here. Okay. There we go. Yeah. I'm doing this because I'm suspecting integer overflow somewhere still. I have not even thought about it, so I'm not sure. Probably because it's a very different number now all of a sudden. Yeah, okay. So that was an integer overflow somewhere. So yeah, that is day 12, part 2. Using a C# dictionary, which is a cool approach. Yeah, let's first recap and then I'm gonna think about some next steps. So for part 2 at least, what did we do? We rewrote my initial brute force thing. We created this replicator that multiplies our inputs by 5, so we get a much bigger input and a much bigger search space. And then we rewrote the entire algorithm to not generate combinations and filter only the valids, but to just count the number of valid combos. It's almost the same algorithm, but not quite. And it's way too big of a wall of text. I would never check this in production code, but for advent of code, this is great stuff. So what did we do? We used memoization to speed up the algorithm significantly. And memoization is a very expensive word for putting intermediate results in a dictionary and looking it up before calculating it. So there you have it. We are using a mutable C# dictionary. I'm gonna see if I can rework this to something purely immutable, because that's my self-imposed constraint for advent of code in F#, but I'm not sure if I'm gonna get there. We'll see, maybe in another video. So anyway, I'm memoizing, and then I have this very dense method that does the actual logic. And it's actually pretty complicated with a lot of edge cases. I'm thinking, are some of those optimizations that are not essential? I don't think so. If we don't do these boundary checks and is the next thing an empty spot, I don't think the algorithm is even correct. So if you are solving these problems as well and you have a better approach than this massive dense pattern match within a pattern match within a whatever, I am very interested in your solutions, so please shout out in the comments below. I'm going to have a long and hard think about reworking this to a purely immutable variant. And if that works out, I will get back to you. If it doesn't, I will not get back to you, but I'll keep continuing and hammering out these advent of code puzzles in F#. But anyways, that's all I have for day 12. Thanks for watching and see you next time. Bye bye.